Yeah, you see. So yeah, you can go ahead and share your screen, Raman.
Right. Can you see this?
No, maybe Gabo, you might have to stop sharing.
I can see it.
Okay, yeah, I can see it now. Okay, great. Go ahead, Raman.
Great. Thanks, Glenn. Right. So first, thank you to the organizers for organizing such a great workshop and for giving me the opportunity to speak. And also for everyone in the audience for persisting through to the last talk of the last session. So today I'll be discussing some work in which we develop effective Landau-Ginzburg type theories for a large class of clustered non-abelian quantum Hall states like the Read-Rezayi states, making use of these recently proposed Chern-Simons-matter theory dualities. So this is work that was done in collaboration with Hart Goldman, who was a group mate and now postdoc at MIT, with our advisor, Bardo Fradkin. And so if you're here earlier in this week, you'll have heard Hart's talk in which he spoke about how we can use some of the techniques I'll be discussing to develop effective field theories for more exotic, sort of pure Fibonacci quantum Hall states. So in this talk, I'll be discussing our sort of earliest work in the series, in which I'll try to provide a complementary view of how we can use these dualities to construct theories for the large landscape of clustered non-abelian states, focusing first on the Read-Rezayi states and then eventually generalizing to these so-called non-abelian spin singlets. So first, just to set the context, one of the sort of most exciting prospects in quantum Hall physics is the potential for realizing non-abelian topological order. So just as a reminder, in these non-abelian states, when we braid these anyons, rather than picking up just a simple U1 phase factor, the braiding of non-abelian anyons generically results in a unitary rotation of the wave function within some degenerate subspace, which is a result of the sort of topological degeneracy associated with these different non-abelions. And so for these reasons, these non-abelian quantum Hall states are of interest in theory for practical applications to topological quantum computation, but also just from a basic physics perspective, they provide physical realizations of non-abelian Chern-Simons theories, which is of interest in its own right. And so in the quantum Hall context, there's a range of non-abelian states which have been proposed, and in particular, some which are potentially experimentally relevant. So in particular, the most famous family of these non-abelian states are these Moore-Reed or Pfaffian states, which realize SU2 level 2 topological order, where this is sort of the Chern-Simons gauge group and its level, which support Majorana and Ising anyons. And as we've seen earlier this week, there's now mounting experimental evidence from thermal Hall conductance measurements for the existence of some state within this sort of family of Pfaffian states, which supports this Ising anyon. And so an example of the class of states that we'll be interested in this talk are sort of the Read-Rezayi states. And so these are generalizations of the Moore-Reed states to more exotic topological orders, which can support, in particular, more intricate non-abelian anyons with more interesting fusion rules, such as the Fibonacci anyon, which is of use for these topological quantum computation applications. Although we have less sort of experimental evidence for these kinds of states, there are numerics which suggest that the plateau seen at 12/5 could be a viable candidate to observe this k equals 3 Read-Rezayi state. And so starting with the sort of seminal work of Moore and Reed, we have fairly systematic methods of generating trial wave functions through conformal field theory methods for these non-abelian states, which have provided us a lot of intuition for the properties of these exotic systems. But what is lacking is an equally systematic understanding of the actual dynamical mechanisms which can give rise to these non-abelian quantum Hall states starting from microscopic electronic degrees of freedom. And so this is the kind of question that we're going to be trying to address in this talk. And more specifically, what we'll want to try and understand is whether we can understand the emergence of these non-abelian states starting from composite particle descriptions. And so with that, what I have in mind specifically is something in analogy with the picture that we have for the abelian fractional quantum Hall states. So just as a reminder, for these abelian states, we have this exact mapping of abelian flux attachment, which takes us from a system of electrons to either systems of composite fermions and composite bosons. And the remarkable feature of this mapping is that we can explain these strongly correlated fractionalized abelian quantum Hall states of electrons at the mean field level as either integer quantum Hall states of these composite fermions or as condensates of composite bosons. And so the hope is that one can try to develop a similar composite particle picture for these non-abelian states. And as it turns out, doing so is actually rather complicated for the sort of full spectrum of non-abelian states. So just to motivate, as a reminder, why this is difficult, we can contrast these family of Moore-Reed states with the Read-Rezayi states. So for the Moore-Reed state, we know, for instance, there's sort of a very simple picture for its emergence at a composite fermion picture. So if we look at half filling of electrons, for instance, we can apply this abelian flux attachment procedure to get a system of composite fermions. And then in mean field level, at half filling, these feel a vanishing magnetic flux. And so if we assume that they undergo P plus IP pairing, the resulting topological superconductor of composite fermions describes the expected sort of SU2 level 2 up to some mu1 factors topological order of the Moore-Reed state. And so what's appealing about this picture in particular is that this matches the intuition that we have from the trial wave function, which was originally proposed by Moore and Reed. So in particular, this wave function constructed from the sort of appropriate conformal field theory correlator has some Jastrow factor, which is indicative of the attachment of two flux quanta in this composite fermion picture. And there's this sort of Pfaffian prefactor, which is the same form factor for P plus IP superconductor. So somehow it turns out that the wave function is in fact sort of at some level encoding the dynamics within this composite particle picture of how this Moore-Reed state can emerge. So in contrast, if we try to look at more exotic non-abelian states, such as the Read-Rezayi sequence, this kind of picture becomes more difficult to develop. So in particular, if we look at the sort of trial wave function, which is proposed for the Read-Rezayi sequence by Reed and Rezayi, what it contains is a Jastrow factor, but also a correlator of sort of ZK pair fermions rather than Majorana fermions. And sort of the physical content that we should extract from this wave function is that it only vanishes if we bring k plus 1 electron coordinates to the same point. So this standard sort of picture of what this wave function is describing then is a state in which electrons are forming clusters of k, as opposed to a state characterized by the pairing of some composite fermion object. And so from this picture, it's sort of clear at two levels why it's difficult to develop composite particle pictures for these more generic Read-Rezayi states, but also more general non-abelian states, which are characterized by this clustering. So first, because these wave functions suggest clustering, it seems difficult to access sort of these non-abelian states within a composite fermion or composite boson picture, since we don't have a simple mean field picture for clustering, in contrast to the sort of BCS picture that we have for a superconductor of composite fermions. And also at a sort of more basic level, these Read-Rezayi states are described by SU2 level K topological order. And so the effective field theory describing the topological aspects of these states will be described by Chern-Simons with SU2 gauge fields at some level K. And so if we start with some composite fermion or boson picture, which involves abelian gauge fields, it's not at all obvious how any kind of interactions between the composite particle objects can generate these non-abelian gauge fields at higher level. And so I'll note that there's been sort of past approaches to investigating these Read-Rezayi states and other more clustered non-abelian states, including parton constructions in which these non-abelian gauge fields emerge naturally. But the sort of goal of the talk today is that we want to try to stay close to this composite particle picture and try to understand within that composite particle sort of framework, whether we can access these clustered non-abelian quantum Hall states. As it turns out, we can make progress in this direction by making use of these recently proposed Chern-Simons-matter theory dualities from the high energy literature, which I'll review briefly in a moment. But sort of the basic idea of the construction that I'll be presenting is as follows. So after sort of reviewing this wave function picture again in more detail, what I'll show is that we want to look for sort of these non-abelian states within some multi-layer system, starting with some sort of multi-layer abelian state, which can be accessed through a composite boson description. And what these dualities will afford us is essentially a generalization of flux attachment to a sort of non-abelian version. The idea being that we'll be able to map the abelian composite particles to theories of sort of composite, non-abelian composite particles coupled to non-abelian cage fields, which we'll call sort of composite vortices. And so this addresses the two problems on the previous slide in that these dualities allow us to explain the emergence of these non-abelian gauge fields, and also the sort of interactions between the composite vortices in this dual description will correspond to more sort of intricate interactions in the original abelian language. And so it'll be more transparent in this dual language how we can access these non-abelian states. And so what we'll end up doing is developing a general scheme to construct sort of bosonic Landau-Ginzburg type theories for both the Read-Rezayi states, which are described by SU2 level K topological order, but we'll also end up generalizing this to more exotic states, which are also characterized by clustering, but have multiple components. So these include, for instance, non-abelian spin singlet states, which can be realized in sort of spin unpolarized quantum Hall systems. Okay, and so with this sort of setup of where we're going, let me start by first motivating the kinds of parent theories we'll be needing in order to access these non-abelian states. So as it turns out, there is sort of a convenient way of rewriting the Read-Rezayi wave function, which is suggestive of the dynamics which can give rise to it in field theory description. So in particular, we'll start first by looking at the bosonic K/2 Read-Rezayi states, and then generalize to the fermionic states later on. So the idea, due to Capelli, Georgiev, and Todorov, is that if we have a system of n bosons at filling K/2, we can construct the Read-Rezayi wave function by first splitting these bosons up into k groups and writing down a nu equals 1/2 bosonic Laughlin wave function for each of these groups. We can then multiply each of these wave functions together. And then if we symmetrize over all the coordinates, the resulting wave function is precisely that of the Read-Rezayi state at filling K/2. And so if we take this construction sort of literally, what it suggests is that if we start with a K-layer system with each layer at filling 1/2, then in addition to having in its phase diagram, a phase realizing decoupled nu equals 1/2 bosonic Laughlin wave states on each layer, that by tuning interactions appropriately, we could induce a transition also to the non-abelian Read-Rezayi state at filling K/2. And so I'll just mention as an aside that this kind of relation between these wave functions sort of reflects a kind of coset construction in the CFT that corresponds to a sort of a diagonal embedding of SU2 level K within the K copy CFT for the Laughlin wave function. But the sort of intuition we want to draw from this then is that we want to start with some parent abelian theory describing these abelian states, and then try to find a way, starting from there, to access this non-abelian state. So with that in mind, the setup that we'll take, taking this wave function picture literally, is a K-layer system where each layer we will describe by the Landau-Ginzburg theory for the nu equals 1/2 bosonic Laughlin state, described by this Lagrangian. So sort of unpacking this notation, this n index labels the layer index. These little a-n's correspond to the emergent Chern-Simons gauge fields describing the topological order on each layer. And these are at level 2, describing the UL level 2 order of the Laughlin state. And to each of these gauge fields, we've minimally coupled these scalar fields capital phi, which represent the Laughlin quasi-particles. So when these guys, when we give these a positive mass squared, these phi fields are gapped and correspond precisely to the fractional Laughlin quasi-particles. But if we allow these phi's to condense, then this results in a trivial insulating state. So this precisely gives us a Landau-Ginzburg theory for these nu equals 1/2 states on each layer. And so I just want to emphasize that this Landau-Ginzburg theory is, again, directly related to the original electronic degrees of freedom. So in particular, starting with electrons at half filling on each layer, we can apply the standard abelian flux attachment mapping to get to a system of composite bosons. And then this Landau-Ginzburg theory is just essentially a particle vortex dual of this composite boson theory. That's to say, these capital phi's are the vortices of the composite bosons. And I'm using here sort of relativistic notation, but this is just as a consequence of the fact that the dualities we'll be presenting are sort of presented in a relativistic way. But at the end of the day, we can always take the non-relativistic limit of our construction to describe the non-relativistic emergence of these states. Okay, and so at this level, It's perhaps not quite clear still how we can actually access a non-abelian phase in this multilayer abelian system, since there's still no non-abelian gauge fields. And so to make progress in this direction, we can make use of these recently conjectured field theory dualities that I've alluded to before. So the sort of notation presented here is not so important. The key sort of physical intuition is that these dualities relate gapless theories of matter, either bosons or fermions, to sort of other theories of gapless matter of bosons or fermions. And both dual theories are coupled to sort of either abelian or non-abelian Chern-Simons gauge fields. And these dualities sort of hold only in the infrared. But the sort of spirit of why we want to implement these dualities is that sort of physics which, or for instance, a phase which is not so easily accessed through interactions of matter fields on one side of the duality might be more easily accessed in terms of the dual variables. So as an example of this, by stringing together some of these dualities, one can access the recently proposed Dirac composite fermion duality, which was employed to describe the physics of the half-filled Landau level recently. But for our purposes, the utility of these dualities is that they will allow us to relate conventional abelian composite particle theories, like the Landau-Ginzburg theory that we wrote on the previous slides, to theories of these sort of composite vortices coupled to non-abelian Chern-Simons gauge fields. So explicitly, within this sort of web of dualities, we can obtain this sort of sequences of dualities, which relate this theory of scalars coupled to UL level 2, which is precisely the Landau-Ginzburg theory we wrote down a few slides ago, to a theory of a different scalar, which we'll call a composite vortex, coupled to a non-abelian Chern-Simons gauge field with gauge group SU2 at level 1. And so explicitly in terms of the Lagrangian, what we have on the left-hand side is the Landau-Ginzburg theory we've written. And on the right-hand side, we have this dual theory of these composite vortex fields coupled to this emergent Chern-Simons gauge field. And the statement of the duality is that these two theories both describe the same nucleus 1/2 bosonic Laughlin state in the IR. So in particular, if we condense the bosons on either side, we get a trivial insulating state. But if we gap them out, then on one side we get UL level 2 Chern-Simons, and on the other side, SU2 level 1. But we know that these two kinds of Chern-Simons theories are in fact identical by this sort of level rank duality. Both of these topological orders just contain a single semyon anion. But the sort of, again, key physical input from this duality is that it allows us to sort of generalize flux attachment to a non-abelian version. So starting from this original system of electrons, we can map to composite bosons, then to this Landau-Ginzburg theory, and then finally using this duality to this theory of composite vortices coupled to this emergent non-abelian gauge field. And the key point then is that, or an important point then, is that the composite vortices, these little phi's in theory B, correspond to sort of complicated non-local monopole objects in the language of theory A. And so the upshot of this is that starting with this multi-layer system described by this abelian composite particle theory, we can apply this duality individually to each layer to sort of describe the same system, but now in terms of these composite vortex objects coupled to these emergent non-abelian gauge fields. And so this description of this multi-layer system, these are equivalent descriptions of this multi-layer system, but because these phi's correspond to complicated objects in the original theory A, there's some sort of bound states of monopoles in matter, the interactions that we write down between these different phi's can in principle allow for accessing phases which are much more complicated and not so easy to see in the language of theory A. And so with this in mind, the sort of Landau-Ginzburg theory that we're going to write down is essentially, it takes this kind of form. So we'll have sort of this non-abelian description of this multi-layer system encoded in this Lagrangian LB. And then we have some effective action describing the dynamics of this order parameter sigma, which is essentially the bilinear of composite vortex fields on layers N and M. And so effectively what this is describing is an interaction which is mediating singlet pairing of composite vortices both within and between the layers simultaneously. And so in particular, an important point is that when under gauge transformations on each layer, sigma transforms in sort of a bifundamental way simultaneously between the gauge transformations of on the layers M and N. And so what we're going to call the sort of clustered phase is the one in which sigma attains some expectation value corresponding to the simultaneous pairing of these composite vortices across all the layers, but one such that the individual composite vortices themselves do not condense. So the single sort of particle composite vortex excitations remain gapped, but they form this kind of paired state, which we'll call clustering since they're sort of simultaneously pairing across all the layers. And the important point then is that in this sort of clustered phase, the fact that sigma attains this kind of expectation value, where this one is the identity within this SU2 color space, and this capital M is just some arbitrary matrix, is that it will Higgs the non-abelian gauge symmetry down to some smaller subgroup. So in particular, we had originally these individual SU2 gauge groups on each layer, but because of this expectation value for sigma, at low energies, residual gauge group is simply the diagonal SU2 gauge group. And so practically speaking, what this means at the level of the Lagrangian is that the clustering manifested by the expectation value results in the gauge fields on each layer being set equal to one another. And so the Chern-Simons terms for each of these individual gauge fields on each layer end up adding up together. And since there are k of them, this yields a level k SU2 Chern-Simons theory. And this describes precisely the topological order of the Read-Rezayi state that we were interested in accessing. And in particular, by keeping careful track of the coupling to the external electromagnetic field, one can see that we obtain the expected Hall conductance. And these composite vortex fields, which individually remain gapped, now describe the minimal charge anion in the Read-Rezayi state with the appropriate charge of 1/2. And so just to sort of recap, what we've done is starting from this multi-layer abelian theory, use this dual non-abelian composite vortex description to write down a Landau-Ginzburg theory, which allows us to access this transition between this parent abelian theory to this bosonic k/2 Read-Rezayi state. And so what we want to do now is show that we can extend this construction to describe the full sequence of Read-Rezayi states. And so to understand how to do this, we can again draw some intuition from the wave function picture. So for the moment, we'll just specialize to a bilayer system, in which case the parent abelian theory is just two decoupled copies of the n = 1/2 bosonic Laughlin state, which just describes the sort of 220 Laughlin state. And so a generic way to access, say, fermionic wave functions from a given wave function is to employ this sort of flux attachment mapping at the level of the wave function, which corresponds to adding m Jastrow factors. So when we do this in a 220 state, we access we obtain the m+2, m+2, m Halpern state, which is fermionic, which describes a fermionic or bosonic state depending on the parity of m. And in the same way, again, sort of specializing to k = 2, starting from this bosonic Read-Rezayi state, we can attach these m Jastrow factors or these sort of flux solenoids to access the generic 1/m+1 Read-Rezayi state. And again, by specializing to k = 2, we're just describing the more Read states at this point. And at the level of the wave function, we can access this general Read-Rezayi state either by attaching Jastrow factors or by employing the symmetrization or anti-symmetrization procedure as appropriate to this sort of generalized m+2, m+2, m state. And so as it turns out, this kind of picture at the level of the wave functions has an exact analogy within this field theoretic construction. So again, focusing on this bilayer system that we had for the bosonic states, what we had was this duality between the 220 state, its Landau-Ginzburg theory, with this non-abelian bilayer system. And so at the level of this field theory, we can employ this or enact this flux attachment procedure directly at the level of the Lagrangian. Essentially what it amounts to doing is adding in these additional U1 gauge fields, which act to simply attach additional flux solenoids, m additional flux solenoids to each of the bosons in each layer, in the same way that it works at the level of the wave function. And so what this flux attachment procedure does is map this duality to a duality between the Landau-Ginzburg theory for the n+2m state to a, again, dual non-abelian description, which again has these SU2 gauge fields on each layer, but with these additional U1 gauge fields, which sort of encode this additional attachment of fluxes. And so the important point is that, again, within this dual description, we can just repeat the clustering procedure. It's unaffected by the presence of these additional U1 gauge fields. And what you obtain at the end of the day is this sort of complicated Chern-Simons theory involving U2 gauge fields, which come from combining the SU2 gauge fields with these U1 gauge fields, which essentially describes the topological order of the n=1/m+1 Read-Rezayi or Moore Reed state. And so this notation might not be familiar with this sort of two-level labeling of the U2 gauge field. What's important to note is that this is just a Chern-Simons representation for the Ising topological order, which is multiplied by the sort of U1 level M factor describing the charge sector of the Moore Reed state. And so if we combine this flux attachment procedure for a general construction, what we obtain at the end of the day is a generic sort of parent theory in which to access the most general Read-Rezayi states. So the parent abelian theory now is going to be the Landau-Ginzburg theory in this K-layer system for this multi-component abelian state described by this K-matrix theory, where m=0 returns us back to original bosonic construction. And this is then dual to some sort of complicated non-abelian gauge theory involving these composite vortices on each layer coupled to these emergent non-abelian gauge fields. And so again, just turning the crank in this sort of construction of the Landau-Ginzburg theory for this clustered state, the topological field theory that one obtains at the end of the day in the clustered phase of this non-abelian theory is precisely that for the Read-Rezayi state at the most generic filling fraction described by the appropriate sort of Chern-Simons theory describing pair fermion type excitations. And again, the composite vortices now represent the appropriate minimal charge anyons. So to sort of as an intermediate summary of what we've done, since this involved some sort of technical machinery in the terms of these dualities, is we presented sort of a generic scheme to access generic topological states. So starting with some Landau-Ginzburg type theory for a multi-layer abelian theory, which can be accessed through a composite boson description, which can be motivated in the Read-Rezayi case for by using wave functions, we can dualize it using these non-abelian dualities to an equivalent description in terms of these composite vortex fields coupled to these non-abelian gauge fields. And then the idea is that interactions, which we call sort of clustering in this dual description, allow us to access some more complicated non-abelian state, which is not so transparently accessed in the original abelian theory. And so I guess I should also say that the sort of generic construction that we presented for the sort of most exotic Read-Rezayi states is perhaps not necessarily the most, is not necessarily always sort of physically manifest or physically relevant. It wouldn't make sense to look for 32-layer systems, but this gives us a general scheme, a proof of principle of how these dualities can allow us to access generic non-abelian phases. And so in the remaining time, I'll just show briefly how this can be generalized to other sort of clustered non-abelian states characterized by clustering. So in particular, one generalization of these Read-Rezayi states is to systems which are sort of multi-component systems involving, for instance, spin, which are proposed by Ardon and Schoutens to describe spin unpolarized quantum Hall states, which are observed, for instance, at 4/3 filling. What's important for us is simply that they describe systems with SU3 level K topological order, and that we can construct wave functions for them in the same way that we did for the Read-Rezayi states. So instead of looking at sort of K-layer systems of 1/2 bosonic Laughlin states, we can take a K-layer system where each layer is occupied by the sort of 2-to-1 Halperin spin singlet state. And then by repeating this sort of symmetrization procedure over the coordinates, one obtains this ideal wave function for this non-abelian spin singlet describes the state at filling 2k/3, and is characterized by the clustering of k electrons, where now each electron can be spin up or spin down. And so what we show in our paper is that within this sort of web of dualities, one can derive another duality relating the Landau-Ginzburg theory for the 2-2-1 Halpern state to a dual theory of these composite vortices coupled to an SU3 gauge field at level 1. And so for those familiar with the sort of CFT description of the edge, what this is reflecting is that this K matrix has some sort of hidden SU3 level 1 symmetry associated with the sort of Kac-Moody algebra. But again, one can just sort of turn the crank and starting with the sort of Landau-Ginzburg theory for this multi-layer system, with each layer occupied by this 2-2-1 state, and applying this duality, we can write down some Landau-Ginzburg theory, which allows us to access this SU3 level K topological order. And just to sort of push this kind of construction as far as it goes, just to sort of map out the most generic non-abelian order we can obtain, we can also derive a duality describing the sort of Landau-Ginzburg theory for a generic NF component state, which is a generalization of the 2-2-1 Halpern state, and show that this is dual to some composite vortex theory coupled to this SUN type gauge field, which again, sort of at the CFT level, is a reflection of this sort of hidden SUNF+1 symmetry of the K matrix. And so again, sort of turning this crank of this clustering procedure in the multi-layer system, we're able to access sort of the most generic non-abelian topological order described by an SUN level K Chern-Simons theory, which are just these sort of multi-component generalizations of the Read-Rezayi states. And so, right, so just to sort of—
Okay, you're almost out of time, Raman.
Okay. So yeah, so just to quickly wrap up, what I presented is sort of a generic construction of how we can access sort of Landau-Ginzburg type theories for generic topological orders with SUN level K, starting from the Read-Rezayi states and then working up to these more exotic systems. And so again, the sort of most generic systems that I presented are not necessarily of physical relevance, but what I hope I've sort of illustrated is that these dualities allow us to access more complicated phases, which are not easily accessible in the original composite particle descriptions. And so I'll just sort of end by noting that we can use these kinds of dualities to shed light on these sort of new aspects of quantum Hall physics beyond these kinds of Landau-Ginzburg type theories. So in particular, I noted at the beginning that, or briefly mentioned that there's a dual description of this Landau-Ginzburg theory in terms of sort of a non-abelian generalization of composite fermions. And by repeating this kind of excitonic, this kind of construction for excitonic pairing in a multi-layer system, we can access other sort of generic non-abelian block Wien states. And we can even use these kinds of dualities to access more unconventional non-abelian quantum Hall states, as Hart spoke about on Tuesday, such as this Fibonacci quantum Hall state, which contains solely the Fibonacci enyon as its non-trivial excitation. And so, yeah, so I'll just conclude by sort of just restating that we sort of focused on constructing theories of these Read-Rezayi and clustered quantum Hall states, but sort of the generic message is that we can make use of these new field theoretic dualities to access more obscure regions of the fractional quantum Hall phase diagram. And so with that, I'll end and thank you for your attention.
Thanks for a great talk, Raman. Okay, so the floor is open now for questions